with our second talk of the day by Pichon-Pharabod from the University of Oxford, telling us about numerical computation of periods and monodromy representation.
Thank you very much for the introduction. Thank you to the organizers for inviting me to the seminar. Thank you all for being here. I'm very happy to be giving this talk. Indeed, I'm going to talk about this, and let me first, although we've seen it already in the previous talk, define a little bit what I mean by periods. So a period, for the sake of this talk, you can just understand as the integral of some rational function, a with some p to some power k, integrated over some cycle of integration. And the idea is you can understand this integral as related to some variety, underlying variety, which, as was already mentioned, is defined by the singularity locus of this integral, so this denominator p. And in this talk, I'm going to assume that p is defines a smooth variety, so nothing singular, at least in the beginning. And the idea is that the cycle of integration that you're going to integrate over is going to be related to a cycle on your variety. So for example, if your variety is an elliptic curve, topologically it's going to look like a torus. And one of the cycle of integrations, for example, would be this red one gamma. So you can understand these integrals, which really are just complex numbers, are as something that instead describes a comparison between two different kinds of cohomologies for your varieties, which are of different nature. The first one being the integration cycles, which tell you about the topology of your variety. And the second one being the integrands, the things you're integrating, which are algebraic, the Rham forms on your variety, which are more of algebraic nature. And so these periods, they sort of establish an explicit comparison, the Rham comparison isomorphism between these two cohomology theories, which have different nature. And it turns out that this comparison carries a lot of the geometry of the underlying varieties, which can be seen, for example, by Turin type theorems, which tell you, in the case of K3 surfaces, for example, that two K3 surfaces are going to be isomorphic to one another if they have the same periods. I won't go into the details as to what I mean by the same, but this goes to show that periods are interesting because really they sort of classify algebraic varieties up to isomorphism in many cases. So that's the first mathematical motivation for why you'd be interested in periods. Another one, which we've already seen in a previous talk, is that they appear in perturbation theory and field theory, and most notably in quantum field theory as Feynman integrals. They tell you about Hodge theory. Really, they appear in many different a priori non-related fields of mathematics. For example, they also appear in very deep conjectures in number theory, the Birch-Swinnerton conjecture. So yeah, this gives a lot of motivation to be studying these numbers and looking at them. And the goal for today, for my talk, is to give you a method for computing these periods, numerical approximations of these periods, with very large precision. And what I mean by very large precision is several hundreds of digits, which is way more than anything you would need for physical applications. But the idea behind computing these numbers with such extreme precision is that if you do so, you can recover some of the algebraic invariants of the underlying geometries. You can recover them just from these decimal expansions. And the way you achieve such precision, you need specific methods, and in particular, you need appropriate descriptions of the integrals, and more particularly of the cycles of integration of the integrals. So I won't focus so much on the integrand part of the things, which methods for dealing with these have already been mentioned, for example, ABP relations and so on. Instead, I'll be focusing on how to find explicit representations of the cycles of integration that make the integration step efficient and also good for recovering so many digits. So there'll be a very big focus during my presentation into constructing these cycles of integration. And I want this to be both effective and efficient, which means that I want to be able to tell a computer to do this for me, instead of this way I can deal with many more examples than I would be able to deal with by hand. And I want this to be efficient in the sense that I want the computer to give me a result in a reasonable amount of time. previous works on numerical computation of periods, I want to cite these three main lines of work, although there are other papers on these slides. The first line of work is the case of algebraic curves, which coincide with Riemann surfaces. And for this, we already had an effective algorithm by De Koninck and Van Hoek from already more than 20 years ago. I will go over this algorithm in greater details in the next few slides, because it serves as a nice introduction to what I want to present, which is a generalization to higher dimensions. So the first few papers that dealt with higher dimensional varieties are these papers of Esserhans and Janel and Zink and Van Straten, where they deal with Calabi-Yau varieties, which are obtained as double covers of some projective space ramified along some hyperplane arrangement. And finally, there's one important paper for the sake of what's coming next, which is this algorithm of Emil Sartos for computing the period matrices of any hypersurface, any smooth projective hypersurfaces, and it does so by deformation. The main idea being that you start with variety for which you know the periods because you have explicit formula for them, and you deform it to a target variety for which you want to know the periods. And if you manage to track how this deformation affects the periods themselves, then you can recover numerical approximations of these periods. More concretely, let me focus on one example. Assume that I want to compute this integral here, where the cycle of integration, gamma again, is a closed cycle on the underlying elliptic curve. It doesn't really matter which one it is. Instead of just considering this complex number, you can view it as the value of a specific function where you introduce this parameter t in front of the last monomial here. So now you have a function of periods that depends on t. And this is good because for two reasons. The first one being that we know the value of pi at 0, because if you set t is equal to 0, you obtain something which is very symmetric in x, y, and z. You obtain the Fermat elliptic curve. And there are explicit known formulae for the periods of this elliptic curve. And in general, for the Fermat hypersurface of any dimension and any degree, you're going to have also expression, numerical, exact formulae for these periods in terms of gamma functions, thanks to works of Frédéric Pham and Emil Sartos. The second ingredient is the fact that this function is also a solution to some linear differential equation, called the Picard-Fuchs equation of this integral. And so from these two facts, you know the value of the function that's at a given point, and you know solution to some differential operators. You can do numerical analytic continuation from the point you know to the point you want to know the periods of. And this can be done automatically with the computer thanks to works of these people. And doing this, you obtain a numerical approximation of pi at 1, which is precisely what you wanted to start with. This method is nice because it works in any dimension and any degree, but it has two main drawbacks. The first one is that if you want to apply it to something different than hypersurfaces, then you're a bit stuck because you don't have the starting point that was the Fermat hypersurfaces. So in more general cases, for completed sections, for elliptic surfaces, and so on, you don't have the starting point. At least you would have to work to get it. The second drawback is that the differential operators that need to be integrated, they scale very fast in terms of degree and order with the dimension and degree of the hypersurfaces that you're looking at. And they scale so fast that very fast you're beyond what current software implementations can manage. For example, if you want to compute the periods of some smooth K3 quartic surface, you would need to integrate some operator of order 21, which is not that great, but a very high degree, very high meaning here several thousands. So the idea to circumvent both of these problems would be to obtain a more intrinsic description of the cycles of integration, as I mentioned before. It should solve the first problem because then we don't need to rely on a variety for which we know the periods already, because we can build the cycles of integration, compute the periods from the ground up instead of deforming them from another variety. And it would circumvent the second problem, because instead of now deforming the full variety, what we're going to do is we're going to slice it in smaller dimensional varieties. So essentially, we're going to gain one step in the dimension, which will allowed to deal with these quartic surfaces that we cannot deal with this method of Anderson. So from this idea, a few contributions emerge. This is a bit of advertising for a nice implementation of this algorithm in Sage Math. Left is fun. If you're interested in computing numerical approximation periods, feel free to reach out to me. I'm very happy to help you get it working for you. This method is applicable to other types of varieties, as I mentioned, not just hypersurfaces. It's implemented in several cases, several types of varieties already. Even if you don't care about periods at all, it also gives a way to compute the homology of complex algebraic varieties from a very frontal approach, which is interesting on its own, even if you don't care about, again, these periods. And this method is sufficiently efficient to compute periods of previously inaccessible hypersurfaces, notably these quartic K3 surfaces that I've mentioned. Okay, so as promised, I will go now over the case of curves, which once again is not my work, but this algorithm from this paper of De Koninck and Van Hooy. And let's focus on one example, one concrete example of, again, the Fermat elliptic curve here in the affine plane. So this defines an elliptic curve. And the cycles of integration we're looking for in the case of curves are one cycles lying on it. And what we're going to, so one cycle on the curve, you can just understand as a loop which lies in your curve. And the idea is we're going to look at a projection from the curve to the projective line. And this is, and the reason why we're doing this is that the image of a loop is going to be a loop, and representing loops in projective line is rather easy. And the question now is, can you go the other way? Can you start from a loop in the projective line and lift it back up to obtain a cycle on your curve? So before focusing on loops, maybe it's wiser to first consider paths, which are easier. So now the question is, I have a path that goes from T1 to T2. Can I lift it back up to a path which lies on the curve? And in order to understand this, we have to understand sort of this fibration structure induced by this projection onto the projective line that we've done. So if we look at the fiber of a given point, this amounts just to taking the equation here and replacing y by t times 2x plus 1. And you see that you get a cubic equation in x, because t now is a fixed parameter. So you fix t, you get a cubic equation in x, and you see that generically, for generic values of t, this cubic polynomial is going to have three distinct solutions, represented by these three Greek points here. And moreover, at these 3 points, they're going to deform continuously with respect to the parameter t as you move it downstairs. There are a few bad points, finally many bad points, which are called critical values, which are the non-generic values for t, where precisely you get less than 3 points in the fiber, because your polynomial equation has a double or even triple. But the point is, as long as you avoid these red points, then you can start from any point in the fiber, and there's a unique way to lift any path in the projective line to a path on your curve. So what happens now when you consider loops? Well, the same thing happens. You have you take a loop that's pointed at a base point at T1. You have these 3 points here, and as you move the parameter downstairs, the 3 points in the fiber are also going to move. And in particular, any point in the fiber is going to be mapped onto another point in the fiber, but not necessarily the same. In particular, you're going to get a permutation induced by the deformation of this loop, and this permutation is what you call the action of monodromy on the fiber. This is something you can compute quite explicitly using a computer, because you know how to compute roots of polynomials, and then it's just about tracking these roots when you move the points around. You can tell a computer to do this, and you can tell that computer to certify this computation. So this is something you can compute explicitly in the case of curves. So now if you try to lift this loop, the question again is, does it lift a loop or does it not? If you start from one of the points that does not get permuted, then yes, it does lift a loop. But the idea is that if you choose a basis of these loops that are simple loops around the critical value, so they go around only one critical value and only once, then lifting this loop to a loop is not interesting because the initial loop you can contract to a single point. So this will also be true once you've lifted it into the algebraic curve. So from the point of view of homology, this cycle here obtained from this green loop is 0. What's interesting is what happens with the other points. And again, thanks to work of Lefschetz, we know that if you take a simple loop, actually the permutation that's induced by the monodromy is not going to be anything possible. It's going to be something quite specific. It's going to be a transposition of 2 of the points in your fiber. So really, if you start from one of these simple loops, there's a unique thing which is interesting from a point of view of homology, unique lift of this loop, which is this path, which does have boundary, but so it's not really a loop. It's not really a cycle on your curve, but it's still interesting because it has it defines a non-trivial relative homology class of your curve relative to the fiber above the base point.
Excuse me?
Yes.
Does it not turn back into a loop if you do a double cover? You go around. Because here at least.
Yes, but then you get the same problem. So if you do twice the circle, then you can it will close off. You will obtain twice this thing. Well, you will obtain 1 time this thing, and you will then add back to it its opposite. Which means that again, from the point of view of homology, this is not interesting because you can still contract everything to 0. However, this is a very good point because you can take several of these dark green paths. Actually, you give they're so nice that you give them a name, call them thimbles. Each critical value has a single thimble, as we've seen. And the idea is you can take thimbles from different critical values and glue them back together to close off the boundary. So for example, here we have 3 critical values around which we have 3 different simple loops. Each simple loop has its own thimble, described here. And you can see that if you glue the thimbles together, then the boundaries match, and you get something which is closed now in your algebraic curve. So the nice thing here is that actually you can recover the entirety of the space of 1 cycles of your curve by doing this. So you take thimbles, you glue them together in this manner, you will obtain a bunch of 1 cycles, and these are going to generate the entirety of the space of 1 cycles of your curve. And concretely, this is just linear algebra. You're just taking the kernel of some boundary map. And you know what the boundary of the thimbles are, because it's just the difference between the 2 points that does not get transposed. So you can recover this from the monodromy, and I've told you how you can compute the monodromy. So this gives you an algorithm for computing the 1 cycles, and we're going to see also the periods of these curves, which goes like this. First, you start from your curve, you pick a fibration over P1. You compute the critical values in red here. And for each critical value, you compute the simple objects. For each of these loops, you can compute the action of monodromy, which is going to be this transposition of 2 points. This gives you the boundary of the corresponding thimble, which is just going to be the difference of the 2 points that get transposed. Once you have this description of all the thimbles and their boundary, you can do this gluing, and you obtain a basis of the space of 1 cycles. And this description of the 1 cycles is very nice for integration, because what you've effectively done is parameterize your 1 cycles as lifts of loops in the projective line. So if you want to compute the periods, all you have to do is a line integral in complex plane. And there are numerical methods to do this very efficiently. So let me show you a demonstration of this algorithm for the exact curve that I had in my slides. So the Fermat elliptic curve given here. It goes like this. You say it's a hypersurface defined by this equation. Here I'm specifying the fibration to match what we had in the slides as well. And then you can just compute the periods. And in roughly 4 seconds, you obtain this 2x2 matrix, because it's an elliptic curve in this case, of periods. And all the digits that you see here are actually correct. What this means here are the bounds of precision. So we've literally computed the periods with 290 certified digits of precision. You can ask the algorithm also. So it did all of what I mentioned in my slides under the hood, but you can ask it for more details. Here is the projection that I mentioned. Here are the critical values in red. It shows in the base point in blue here. It made this choice of simple loops around all the critical values. It computed all these monodromy actions. So I said there were permutations. You can see that these are all transposition matrices as promised. From the transposition matrices, you recover the boundaries of the thimbles, which are just the difference between the 2 points that get permuted. So for example, for the first one, the first and the third point get permuted. So their boundary is the difference between the first and the third point. From this boundary, you can just glue the thimbles together again. And you see that you obtain a basis of the space of 1 cycles, which are obtained as lifts of 2 loops, the first one being this one, and the second one being this one. And now what you've effectively done is parameterize the basis of 1 cycles for your elliptic curve. And then to do the integration, you can rely on some Picard-Fuchs equation that you have to integrate, and you obtain the same matrix as I mentioned. So this closes off the case of curves, everything I wanted to mention about curves. So maybe now is a good time for questions about this case. Otherwise, I'm going to, yes?
Could you please repeat how you get this true yellow cycle in the demo? One that gives the nice basis, like these and these ones?
These ones? So the idea is I start from a basis of all so yeah. For each of these red points, I'm going to have a loop, right?
Yeah.
The idea is then I have a description of the 1 cycles of my curves in terms of these loops, which are, so for example, the first column here corresponds to the first loop, the second column to the second, third to the third loop, and so on. And then I'm gluing them. So literally, I'm taking the concatenation of these loops, which is how I obtain these. Does this answer your question, or? Okay,
so in the way you do the concatenation comes from the matrix you have below?
Yes, exactly. The matrix below tells me what linear combinations of the thimbles I should take, which means what concatenations of these simple loops I have to take.
Okay, thanks.
Any other question? Okay.
Sorry.
Yes.
So just something that confuses me, because you said you didn't need to know this 5-0, but you still need a boundary condition if you're integrating your Picard-Fuchs equation. So
no, because these are loops. So
you're integrating the period. Okay, yeah.
I'm integrating something over a loop that does not have boundary.
Okay, because yeah, I was confused because at the end you mentioned the differential period, but okay.
Yes.
Completely the integral explicitly.
So what I need are the periods of the fiber, well, yeah, I'll go over this in more details later. But you're right that there's something going on under the hood which I'm not mentioning. Okay, so now I'm going to talk about a generalization of this to hypersurfaces. So how do you generalize this not to curves anymore, but to higher dimensional hypersurfaces? So these are ideas that are already more than a century of years old, but they were only made effective, as far as I know, in this paper with my advisors, Pierre Lérez and Pierre Vanov here. So it turns out that high dimensions are very similar to curves in many aspects. For example, you still have monodromy. So the idea is going to be the same as before. You start from, in this case, a surface. Really, you should think of an n-dimensional variety. And you look at a projection onto the projective line. It's still going to have some bad critical values of your projection. And the fiber now is not only going to be a finite set of points, but instead it's going to be a full curve, which I've represented with this elliptic curve, this torus here. But this curve is again going to deform continuously with respect to the parameter you choose in base. So as you move the parameter along this loop here, the torus sort of deforms, right? And now if you look at a one cycle which lies on this curve, then it's going to follow this deformation as you move the parameter along, and you can see that the cycle, red cycle here, sort of follows along, and then it gets mapped to another one cycle, which is not the one you started with. And so this means that if you look at what the deformation does to the space of one cycles, is it's going to induce some isometry of this H1, which you call, once again, the monodromy along the loop L. This monodromy is going to be encoded. So one of the ways, I'll go into more details later on, but one of the ways you can compute this is through a differential equation, again, the Picard-Fuchs equation of your family of elliptic curves. I'll give more details later. The point is, if you start from smooth hypersurface and the projection is generic, then you're only going to get monodromies that are of a very special shape. In the same case as for curves, you only got transpositions. In the case of higher dimensional varieties, you're going to get monodromy matrices, which are always of the shape the identity plus something which has rank 1 and which is primitive. In the case of elliptic curves, what this means is a simple Dent twist, which is something that looks like this. This animation is when you go through the critical values. You pinch and you obtain a singularity. You let the curve gain to a singularity, and then the Dent twist is going to take the cycle that survived this pinching and give it a twist along the one that has vanished, the vanishing cycle. So now for surfaces, we're no longer looking for one cycles on a variety, we're looking for two cycles. A two cycle you can understand just as a two-dimensional real manifold, submanifold of your variety. And one way to obtain such a two cycle, which is very analogous to what happened in the case of curves, is to start from a cycle on the curve above some base point, and to track what it does when you deform the parameter along the loop. What it's going to do is it's going to cut out this sort of pink tube here that you can see. The cycle that you land at may not be the one you started with, and because precisely you acquire some monodromy. But if it does match, then you can close up this tube and you obtain a proper two cycle of your variety. This is a very nice description of a two cycle for the sake of computing periods, because now if you want to integrate something on this pink tube, all you need to do is two linear integrals. The first one being the period of the curve above the base point along this cycle here, which I've just told you how to do because this is now just the period of a curve. And the second one is going to be an integral along this loop here, which is again just a line integral. So these are just two line integrals, and we know how to compute these numerically very efficiently. So here is the comparison for general dimension hypersurfaces compared to two curves. So now you're looking for n cycles, and you can obtain certain n cycles by extending n-1 cycles along loops. The monodromy along a loop is going to induce an isomorphism of the space of n-1 cycles, and your extensions are going to close off precisely when the monodromy along the same loop matches the cycle you start with to itself. If this hypersurface is smooth and if the projection is generic, then all the singular fibers are very simple. This is why they have this simple monodromy structure. And there's a single thimble, so a single interesting lift of a simple loop around each critical value per critical value. And you can play the same game of taking all these thimbles and bringing them back together. And it turns out that you obtain almost everything, almost every n cycle of your hypersurface by doing so. However, there are some complications. You don't get everything. You're missing classes that may lie entirely in the fiber, and you're also missing classes that could be obtained as sections of your projection. However, for the sake of computing periods, it turns out that this fiber and these sections are not so interesting because their periods are zero. So really the interesting part is something in the middle here, which is precisely what you can generate with extensions. And it's interesting because the periods of everything else are trivial. And so this middle part is also known in the literature as the parabolic homology or cohomology of your fibration. So this is all and good, but there's something which I haven't told you, which is how you actually compute the monodromy. So in the case of curves, you could do this by tracking points, but in higher dimensions, this becomes a harder problem, because if you want to just look at the picture, it becomes very quickly too complicated to track by hand, and telling a computer to do it might not be efficient. But as I've mentioned, you can compute monodromy through the Picard-Fuchs equation that describes your family of n-1 dimensional varieties of the fibers. So let me first tell you how you compute the monodromy of differential operators efficiently and with guaranteed bounds of precision that are very. So this is work of, again, the Chinovsky brothers, which was later refined by Johannes van der Hoven and later again by Mark Lesser. So it relies on something that you probably all know quite well, which is the Taylor expansion of smooth function at a point, or analytic function at a point. The idea is you assume you know your function at some point alpha, and you know this function and the first few derivatives. What's really nice about this formula is not so much, well, the left-hand side you all know, but what's really nice here is this right-hand side, which tells you that as long as t is sufficiently close to alpha, and sufficiently here means twice closer than the closest singularity, then you can bound the difference between the Taylor approximation and the actual value of the function by something that decreases exponentially fast with the number of terms that you put in this sum. This is nice because we're a solution to some linear differential equations. Once we have the first few derivatives, we can generate as many as we want. And also, interestingly, here, you get a polynomial factor here in front of it, which depends on m, and this polynomial turns out to be effective, which means that you can prove precision bounds using this formula. So the idea is you compute the value at alpha. Well, you assume you know the value at alpha, and you use this Taylor expansion to move slightly along the path that you want to compute the analytic continuation of. And you obtain the values at t. And now at t, you have a different radius of convergence. And in particular, you can do another step which goes a bit further than what you could do before. And now you arrive here, and then you can iterate this along the path until you reach your destination. So this tells you how to do numerical analytic continuation of solutions to differential equations. And this method is also nice because it has linear complexity in the number of digits that you obtain. So if you want to increase, if you want to double the number of digits that you have, you only have to double the amount of time that you spend, which is much better than, for example, Monte Carlo methods, where if you want to double the number, well, rather, if you want to obtain one more digits, you have to more than double the number of points, sample points that you take. Okay. So how do you use this to compute the monodromy on cycles? And the answer is that you use the periods of the fiber itself. So you use the period matrix of the fiber that is one dimension less than the period matrix that you want to compute. So you have sort of this inductive reduction where you're trying to compute the periods of your n-dimensional varieties and you rely on periods of n-1 dimensional varieties. So you start from this period matrix where here the gamma j describe the basis of the one cycles, and you assume that omega t is a rational form, an algebraic form for which the derivatives generates your cohomology. Now, all of these are going to be solutions to some differential equations, the Picard-Fuchs equation, or rather the Gauss-Mann connection. And so using this, you can do numerical analytic continuation along a path. And what you obtain in the end is another matrix, phi tilde, which is also a period matrix of your fiber. But what's really nice about this is that now you can decide that your algebraic forms are actually depend only rationally on T, which means that they have no monodromy, which means that the monodromy that you see acting on the period matrix only acts on the cycles of integration. Of course, by linearity, you can do this. What's important here is to note that these coefficients, the ckj's, are all going to be integers. And the reason they're integers is because the homology has an integral structure. So it doesn't make sense to talk about half a cycle. If you deform one cycle, you're going to obtain one cycle when you come back after the monodromy, which is why these numbers are going to be integers, because you have an integral basis of the homology. You can, of course, rewrite this as a matrix equation. And in particular, you can then multiply by the inverse of the period matrix on the left, and you obtain this very nice equation where here on the left, this product is a product of transcendental matrices for which the entries are periods, which you can only hope to obtain finite decimal expansions of. Whereas on the right-hand side, you get some integer. And it tells you that if you manage to do this computation here with precision greater than 1/2, or smaller than 1/2, I guess, and then you recover these integers exactly, and this is a proof that that the matrix that you've computed is correct. So this tells you how to compute monodromy, and from monodromy you recover the boundaries of the thimbles. From the boundaries of the thimbles, you know how to glue them together, and then you have this inductive approach for computing the periods of any hypersurface in any dimension. From these periods, you can recover some algebraic invariants. For example, if you look at quadratic equations in projective 3 space, these define K3 surfaces. Sorry. And as K3 surfaces have some invariants attached to them, which is the Picard rank, and it turns out that you can recover this Picard rank from the period computations. For example, this equation here is the equation for a K3 surface, which, at least from the period computation, seems to have Picard rank 2, if I remember correctly, or 3 or 5. I'm not sure which one. You can sort of see why the Picard ranks 2, 3, and 5 were missing in the search for explicit quadratic equations for all possible Picard ranks for K3 surfaces by Pierre Levez and Emma Santos. And one of the reasons why, for example, they could not compute the periods of this is that this equation is quite far in terms of number of monomials from the Fermat equation. So their method is only well adapted for quartic equations that are very close to Fermat. Oops. This table sort of does a comparison of the efficiency of the two algorithms. And for example, what I just mentioned here, so Numerical is the implementation of Pierre Levez and Mosatos. And you can see that, for example, for the quartic, it's instantaneous, of course, because the periods of the Fermat quartic are going to be hard-coded in that code. But as soon as you start adding more and more monomials, it takes more and more time. And already at 4 monomials, you get an example where it takes more than reasonable amount of time. Also, what can happen is that the Fuchs equation becomes so large that the memory of your computer explodes. Compare this to the method I've just presented, which itself is completely agnostic to what your defining equation looks like. So, of course, in cases close to Fermat, it's going to perform much more poorly. But as you increase the number of monomials, it's not going to get worse at any rate. And the fluctuation that you see here really only comes from the fact that the choice of fibration that you make has an impact on performance and is sort of random. You could pick another fibration for all of these cases and probably improve the performance. And so we have solved one of the main difficulties for computing these periods, which is the key thing was that we described these cycles of integration explicitly as more intrinsically to the fiber instead as the deformation of something bigger. So what we've really gained is one step in dimension. But the bottleneck for accessing higher and higher dimensions and higher degrees is still going to be the degree of the differential operators. Because now if I wanted to instead compute the periods of some quartic threefold instead of surface, I would need to integrate the same operators that the algorithm M-Recital relies on for the periods of quartic surfaces. So we've just gained one step in the dimension. Okay, so before I showcase this on a concrete example, let me mention one application, which I will also show you some code for, which relies on this very well-known fact in algebraic geometry that if you take a cubic surface, you're going to have 27 lines on it. So this is represented here. So this is the Clebsch surface. The animation is like this passing here. And this Clebsch surface is very nice because all the 27 lines are actually real, so you can represent them. And they sort of look like this. The homology classes of these lines are characterized entirely by their intersection numbers, namely the fact that they have self-intersection -1, and they have to intersect the hyperplane section in precisely 1 point. And the idea is that now if you have a family of these cubic surfaces, these lines are going to deform continuously with the parameter of your family as well. And so you're going to, again, get an action of monodromy on these lines. And this is something you can compute explicitly if you know how to compute the action of monodromy on the space of 2 cycles of your surface. The full monodromy group of all cubic surfaces is the same as the full group of automorphism, preserving the intersection pairing of these lines, and it's the full Weyl group of E6. This is a well-known fact, but this is something that with the methods I've just presented to you, you can just compute. Instead of doing this, I'm going to focus on a more recent problem, which is that now instead of considering all possible cubic surfaces, you're going to consider cubic surfaces which have defining equations that are invariant under some symmetry action. So for example, you could ask what happens if now I only look at cubic equations where which are invariant under transposing and any permutation of the variables. Turns out that there's a recent theorem of Rham that shows that actually the group monodromy group in this case is much smaller than the full Weyl group of E6. The Weyl group roughly has order 51,000, whereas this one has order 4-ish, the Klein group, the Klein 4 group, sorry, which is again surprisingly. So this is something you can compute explicitly using these methods. So let me first go over the computation of the periods of cubic surfaces. So this is before we looked at the monodromy. So let's say I'm interested in the cubic surface, which has this equation here. I pick a fibration. The fiber above the base point that I've chosen is going to be given by this cubic equation, which now describes an elliptic curve. So this is a cubic equation with only 3 projective variables. I can compute the periods because these are the periods of just a curve. And I get this matrix here. These are the critical values of my projection of my surface onto the projective line. And again, I've computed for each of these critical values a simple loop. This is the differential equation that characterizes the deformation of the fiber of this elliptic curve. You can see that it gets quite ugly quite fast, even just in terms of what these numbers are. These are very big integers. And it only gets worse when you increase the degree and dimension of the surface. But now you can compute the action of monodromy on the solutions to this differential equation, and you obtain this matrix here. Here I've computed it with a certified bounds of precision, but for the sake of showing it, I've forgotten the precision bounds, but you can be confident that the first few hundred digits here are going to be correct, at least internally. Here are the periods of the fiber, and what I claim is that if you conjugate the periods of the fiber if you conjugate the action of monodromy on the solutions of the differential equation by the periods of the fiber, you should obtain a matrix which has integer entries. You can see that this is the case here. And this is actually a proof that these integers are correct, because it's not shown here, but I've computed these numbers with several hundreds of digits. So I can be 100% sure that the monodromy along whatever loop I've chosen acts on the space of one cycle of the elliptic curve that's my fiber by this matrix in a certain basis, which is again internal to the curve. And you can do this, of course, for all the loops. And you can check that the projection is generic, because now if you remove the identity from all of these matrices, you can see that these are all of rank 1 and are all have all primitive image. It's just a sanity check that you can. So from these matrices, then you obtain the boundaries of the thimbles, which are just going to be the image of these matrices. And then you can pair them up, group them up together to obtain this description of the 2 cycles of your cubic surface in terms of the thimbles. This tells you, for example, the first line, that one of these cycles is obtained by taking the first thimble, which corresponds to this matrix, to the penultimate. And you can see that indeed the image of this matches the image of this matrix. Okay. And then you can compute the periods, and then there's a bit of technicalities. And you obtain this period matrix, which is 7 by 7, which is what you would expect for a cubic surface. And this is something I've computed again, as promised, with 300 digits of precision, of guaranteed precision. Okay, so now let's look at the family of these cubic surfaces. And to look at the family generated by these 3 polynomials, which are the ones that are symmetric under all these variable permutations. I'm just going to take a random one-parameter family that lies in. I can compute the differential equation for this family, which again is quite ugly, which is why I had hidden it. But it has order 6 and degree 49, which is a non-variable, really. The computer manages this just fine. Then there's a bit of technicalities. These are the critical values in red, base point in blue, which correspond to the fiber for which I've already computed the periods. Then I compute these transition matrices, which are the numerical analytic continuation of the solution by differential operators. I recover the period matrices. I recover the monodromy matrices by doing the same trick, except now my matrices are 7 by 7, but this is an integer valued matrix. Again, for the sake of showing it, I've reduced the precision to 10 or 20 digits, but really there's much more. And here are all the matrices for all the loops. Now it's just about finding these 27 lines, which I can do by computing, finding the classes that have the correct intersection pairings. And I find these 27 lines as expected. The first 5 are given by this. So this is a coordinate vector in whatever basis of the space of 2 cycles of my surface I've chosen. This is the intersection or the incidence matrix of all these lines. In case you want this is data that you just have. And then it's just about applying these monodromy matrices on these coordinate vectors that I found and identifying them back again as lines. And what you get in the end are all these permutations, which all correspond to one of these loops. And this tells you, for example, that the first and the second line get permuted, and the third and fourth, and so on. Of course, the numbering is completely arbitrary. And then you look at the group generated by all these matrices, and you find that it has rank order 4, and then you can ask also what precisely it is. And it turns out to be the type 4 group. Okay. So you can do this for cubic surfaces symmetric under all permutations of your variables, but you can also do this for cubic surfaces that have equations that are symmetric under any group of linear automorphism of this projective free space. And for example, this table are all the subgroups of this group of permutation of all the variables up to conjugating. And you can see that there's a wide variety of monodromy groups that appear, which have cardinal that varies as well. So this is work with Simon Tellen. Like this. Oops. And this is the line group E6. Okay, so all I've presented to you right now relies on the assumption that the variety that you were working with was smooth, because if it's smooth, then you can find these generic fibrations, and in particular, you're sure that you can reconstruct the entirety of the space of n cycles of varieties. However, it's not always the case that you want to deal with smooth varieties. In particular, I'm going to show you how you might be able to circumvent some of the issues that you get when you have singular varieties by focusing on the case of elliptic surfaces. So an elliptic surface is a surface which has a fibration over P1, which is exactly what we want. The fibration is by elliptic curves. However, the fibration, it's given to you. You don't have a choice, and it's also rigid, which means that you can't deform the fibration to obtain something generic. You're stuck with this fibration. So to give you a concrete example, let's look at the Apéré surface, which is related. So this is a rational elliptic surface that's related to the irrationality proof of zeta of 2. It's defined by this equation. And the starting thing is the same. So here the parameter is t, the fibration parameter. And you start the same way. You compute the set of critical values, which are the 3 points. You pick a base point, which is not one of these 3 points. You compute a basis of loops. And then you compute the action of monodromy along these loops. These are 2 by 2 matrices because the fiber is an elliptic curve. You get these matrices. And here you can see that these are not going to be of Lefschetz type. For example, if you remove the identity from this matrix, you get something which is not primitive because the image is 4 times something. And here, if you remove the identity, you don't even get something which has. So we have to find a workaround. The workaround that you find is that you can deform the equation of your surface. So now we're deforming the entire surface instead of changing the fibration. What will happen to the critical values is that they're going to move around, and some of them are going to split like this. But the important point is that if you do a smooth deformation of your surface, then you don't change the topology of the surface. So the topology of this deformation is the same as the one you started. And now with this new surface, you do the same computations as before. You compute the monodromy matrices like this. And now you can see that they're all of Lefschetz type. So that this is a generic fibration, and such a deformation, you call it morphification. So now you can recover the entirety of the homology of your new surface of this morphification, and you can relate it back to the homology of the initial surface you were working with. You can see there are some new cycles that appear. For example, there are cycles that in the non-morphified version are collapsed into a single fiber. These are called components of singular fibers. And you also get other cycles that mix up, that connect some of the new critical values that belong to different fibers. Now, what you can prove is that if you look at the sublattice of the homology that's generated by extensions of the initial surface, by components of singular fibers, by the fiber and by the section of your surface, then you get something which has full rank. And this is good because the extensions are the only ones which have non-trivial periods. So for the sake of computing periods, if you're able to compute the periods of extensions and you're able to relate, or rather to explain how this sublattice fits into the larger, into the full homology lattice of your surface, then you've won, essentially, because you can then, by linear relations, relate the periods of any cycle to these other extensions. So you get an algorithm which is very similar, at least in the beginning, to what you had for hypersurfaces. Compute these critical values, these simple loops, the monodromy, you compute the extensions, you integrate the periods. Then you do this morphification and you compute the cycles of the morphification. And you know that now you're going to obtain everything from extensions. And then you relate these the cycles of this emulsification to the initial cycles of the initial surface. And doing so, you recover the periods and a full description of the homology of your initial surface. This allows you to deal with non-smooth varieties. For example, a Feynman graph, the tardigrade graph, which was mentioned already in the previous talk. You can see the very clear resemblance between the graph and tardigrade. It turns out that the underlying geometry, I mean, it's not necessarily obvious. The obvious underlying geometry of this graph is a cubic threefold, and then you can associate this cubic threefold. You can, or rather, can show that it has the same motive in some sense as that of the quartic, as that of a quartic K3 surface, which has a certain number of singularities. But using the methods I've presented just now, well, because it has one singularities, you can find analytic fibration, and then you can compute its periods. And doing this, you can recover some algebraic invariants, notably the Leonce-Every rank, or the Picard rank, it was mentioned in the previous slide. It's the same thing, of this K3 surface. Which, in a sense, in physics terms, I guess, tells you about the number of master integrals that are relevant in this K3 surface. Well, that come from this K3 surface's periods. And the way you do this is just by computing these periods with very high number of digits, and then finding some linear relations between these periods with rational, rather integer coefficients. This relies on this theorem of Lefschetz that tells you that a homology class is in the Leonce-Every group if and only if the periods vanish on this cycle. And this is something you can do explicitly using the LLL. And you can then certify this from a monodromy computation. Yeah, I guess I have a demo. So this is the defining equation of the elliptic surface. So here the kinematic parameters have been chosen more or less randomly. They're random integers or rational numbers. I'm not quite sure anymore. But you obtain this ugly equation, if I can say so, which defines a family of elliptic curves. So this is an elliptic surface. But you can apply everything I've just mentioned. These are the critical values. You compute the same loops. This is the equation that you have to integrate. Again, it's older, smaller than before. It's smaller than before, but its size is already bigger than the previous examples, just because the starting equation was also that. You compute the monodromy matrices, which might take a few seconds. So now, right, it's computing all these 2x2 matrices. You can see the fiber types. If you know about elliptic surfaces, you can see the fiber types from the monodromy representation, and then you can compute the periods, and you get this 22 by 1 period vector. So these are the homomorphic periods of your K3 surface obtained with 200 digits of certified precision again. And then you ask linear relations between these periods, and you find that there are 11 of them, which tells you that the Picard rank of your K3 surface is 11. Okay, and my last slide. To summarize, I've presented to you a method for computing periods of algebraic varieties, which has been implemented in several cases, in particular hypersurfaces and surfaces. This method is sufficiently efficient to recover the periods of examples that were previously out of reach, for example, these K3 surfaces. And you can use these methods to recover, at least heuristically in some cases, to certify certain algebraic invariants of certain varieties that arise in various contexts, namely Feynman integrals, I guess more importantly for this crowd, also number theory and mirror symmetry and so on. That's everything I wanted to say. Thank you very much for your attention. And this book is the book of Lefschetz from 100 years ago, which I got actually Yeah, I think this is the copy they have at IHP. So where essentially many of the ideas I've presented today are already in this book, but now they've been made effective. Thank you very much.
Thank you very much for your talk. Any questions?
Can you use the same strategy to deal with Calabi-Yau threefolds and multi-parameter families?
Yes.
Monodromies?
Actually, the Calabi-Yau threefold that was mentioned in the previous talk, which is a Hadamard product of two elliptic surfaces. There's a bit of theoretical work you have to do, but essentially the same methods work exactly the same. I've not mentioned it here, but it's also been implemented. You can deal with Calabi-Yau threefolds that are obtained this as Hadamard product of elliptic surfaces this way.
And if you take a generic case, I guess you need to have a fibration, like a K3 fibration or elliptic fibration for this strategy to work.
Yes. So you don't necessarily need a fibration in the sense that, for example, for hypersurfaces, if you give me a hypersurface, it doesn't come with a fibration. What you can do instead is force a fibration on it, which sometimes you have to do some blow-ups, but if you're careful enough, you can track what deformations you have to do to your initial variety, and you can you can use some generic fibration on your variety and apply this, and then you have to be careful to see which cycles you have to keep and which are going away. But in principle, it should work. In many cases of Calabi-Yau varieties I've been looking at, they're given as toric hypersurfaces, and then you can just use projection onto one of the variables as your fibration. You're guaranteed to obtain to be able to describe some cycles like this. You're not guaranteed, as far as I know, to be able to describe everything. But in most cases, I've been looking at Calabi-Yau operators. There's this list of ASC, right? In many cases, you can find such a toric model. And once you have this toric model, you can show that actually capture the motive that's described by the Calabi-Yau operator from this variety by using this fibration technique. So in some sense, all the transcendental things that you can obtain when you look at these fibrations, you have to be able to describe it in terms of the fibrations, because that's where the transcendentality comes in. Everything else that's contained in the fibers is not so interesting because it's usually algebraic or blow-ups or something like this. So the real transcendental part is going to be located in this middle part that you can describe with extensions. That's not a theorem, but that's my general take on how these things should go, at least in general.
Maybe just a curiosity, when you talk about the mercification, since the number of critical values are changing when you do this deformation, does it also mean that the rank of the differential equation is changing, or that should be the same? Because I usually think that like the number of critical values should be related to rank, but I'm not sure it's the same here.
So yes, so it depends what you mean by when I said several times the Picard-Fuchs equation, but it's not true that there's a unique Picard-Fuchs equation. There's as many Picard-Fuchs equations as there are cohomology forms in your Rham cohomology. What you usually want to do is you want to find a cohomology form which is such that its derivatives are going to generate the full cohomology. Otherwise, your differential equation will not capture the full monodromy of the full cohomology space. So in particular, if you do this, then the rank, the order of your differential equation is just going to be the rank of this space of cohomology, which if you do a smooth deformation, which these emulsifications are, should not matter.
And so like the fact that before you had this like 1 point with the 1401, it doesn't mean that like above I have the before critical point that all map to the same critical value. It's something else.
So it sort of means that you have a very bad singular fiber above, which is the overlap of all the simple singular fibers that you have once you multiply, which is why you get 4 points here, right? When you go back to the singular surface, these 4 points collide, and instead of a single Dehn twist, you have a quadruple Dehn twist. This is what happened. Really, well, yeah. I guess it depends on the specific elliptic surface to know precisely what happens at the singular point. It might be that the singular points collide together and you get a worse singular point in fiber, or it might be that you have several singular points in the fiber. Yes.
You said that the main bottleneck is integrating the periods of the fibers in this very high order Picard equation.
Yes. So the real bottleneck is also just computing this Picard-Fuchs equation. If you do things generically, then I try to show it a little bit in these code snippets that the size of these equations keeps increasing, and the examples I've shown you are really mild. If you look at K3 surfaces, you get equations that are several megabytes worth of data. So just even computing them is already a hassle, and then integrating them is the next step. If you even manage to compute them, integrating them is also not a good. There's things there's a balance between doing things generically, which is very nice for computers, because computers it is good to have a generic algorithm because then it's applicable to lots of things. But the problem is that then it's not clever about how it does things. And in particular, you might be missing symmetries that could simplify the problems very much. So there's a balance to find between tailored choices for the specific examples that you're trying to deal with, where you use these symmetries to simplify the problems because you know that it's possible to simplify them, compared to having generic methods to deal with these with more problems, but in a less clever way.
Can I make a comment? So physics-wise, so you can have an order. So the differential equation has an order. So the highest degree of the catalyst, and the degree is the degree of the collinear coefficient. So the order is bounded by the number of masters, and it's smaller. Okay. So this one, for example, you can control its score, but the degree is wide because you know that there is a polynomial that implies the highest order differentiation is first that zeros are, it's the discriminant of singular locus, so the zeros are the threshold, so you know where they are, but they are all the apparent singularity. And in fact, even if you have a graph that expects the mutual subset, that get the growth in terms of the derivative order that is light, the degree is more than exponential because of this apparent singularity. So you are really killed by that. And so this is, it's not totally clear how to optimize that part, but if you try to desingularize, then you don't have the apparent singularities, but then you increase the order.
But this is these apparent singularities are also divided as a first order differential equation, or is it just in writing?
No, okay, it's one way to be, but I mean it's related to the optimization of the Gauss-Manning connection. Right, because you just do the way you convert this to first order or these, and so yeah, so this is where there's
learn how to integrate it.
Because these apparent singularities they come from some block in the you know where. So there's a conservation difficulty. In that language, this is where the difficulty is.
Any other questions or comments? Okay. Speak it again. And we resume at 4:30.